Hello, and welcome to Lecture 2 of Electric Current and Resistance in Phys 1201. The title of this lecture deserves a tiny bit of explanation. Voltages can cause currents. We've seen cases where they don't. For example, when a battery is hooked up to a capacitor and the capacitor is fully charged. However, when a voltage is applied across many circuit elements, like wires and resistors, it will cause a current. So in this lecture, we're going to look at what factors determine how big that current is. So I'm going to start off by reiterating something that we've seen a number of times, so I'll do it fairly quickly. We have a potential difference between two plates in a capacitor, and the same potential difference then if you walk around through a wire connected to the plates. And the really relevant thing here is that the potential is high near the positive plate and low near the negative plate. So notice that electrons flow from low potential to high potential, and we've already seen this. But current, or what we often call conventional current, the flow of positive charge, goes the other way. It goes from high potential to low potential. This is one of the reasons it's more convenient to think in terms of conventional current. If you think in this analogy of potential as being like height, then it's convenient that conventional current goes from high to low, just like something rolling down a hill in the analogy. Also note, the electric field points from high potential to low potential. We've seen that in the previous unit. And so that means conventional current always flows in the direction of the electric field. Note that this works whether you're talking about a wire, a metal, or anything else. So it happens this way no matter what the charge carriers are. So for example, in a solution, again, we've already seen that the currents that result from the motion of the positive charges and the negative charges both go in the same direction because the current due to the negative charges is in the opposite direction to the direction those charges move. Both those currents are in the direction of the E field, and again, the E field points from high potential to low potential, and so your conventional current runs from high potential to low potential. But for various reasons, it's sort of time to leave behind looking at capacitors as the primary things that we think about pushing charge through wires. So remember that for a capacitor, the voltage across it is proportional to the charge on the plates. And so as current flows, charge is leaving the plates, and so the charge on the plates decreases. And as the charge decreases on the plates, the voltage will decrease. And so this leads to a somewhat complicated situation because now you have a changing voltage which is driving your current, and it means things are changing with time, your current changes with time, and so on and so forth. So even though we developed a lot of these ideas by thinking about capacitors, because what happens inside capacitors is nice and simple, and it's analogous to just things that happen when you rub things and give them charge and then hold them close together. And even though batteries are very complicated, the way batteries behave in circuits is very simple because they provide a fixed voltage. And again, we have a high voltage or a high potential side and a low potential side. The high potential side is the positive terminal, and everything works as before. The electrons have low potential energy where the potential is high, and vice versa. But if we think about conventional current, it has high potential energy at the positive terminal and low at the negative terminal, and it's running out of the positive terminal and into the negative. And so we can think of the battery as taking charge from its negative terminal and lifting it like an escalator from low potential to high potential, from low potential energy to high potential energy. The battery has stored energy as chemical energy, and so what is going on physically inside the battery when this is happening is that there's an energy transformation from chemical energy stored in the battery into potential energy. Work is being done on the charges as they're moved from a location of low potential energy to a location where they have high potential energy. If you reverse the current and push charge through the battery backwards, then if it's a rechargeable battery, you reverse this and you're converting electrical energy back into chemical energy. If it's not a rechargeable battery, then because the chemical reactions in there aren't reversible, all you do is warm it up. You convert electrical potential energy to thermal energy. I've already made this analogy of potential to height a fair number of times. For example, when we were comparing contour lines on a topographic map with equipotential curves. And so hills can be thought of as corresponding to voltages in this analogy. Since we're beginning to talk about circuits, how can we have a circuit on a hill? Well, one way is a ski hill, right? On a ski hill, your skiers go up on the lift and back down, and they hop back on the lift, and so they're going around and around just like in a circuit. And so you have a skier current that goes around on the hill, and every skier who goes up the hill must come back down. You have a conservation of skiers unless there's a bear standing on the hill eating them or something. So if you go to a ski hill and conservation of skiers doesn't seem to apply on that hill, you should probably go to a different hill. So anyway, you can now look further into the analogy. What's the lift? Well, the battery takes charge from where it has low electrical potential energy and puts it where it has higher electrical potential energy. Similarly, the lift takes skiers from where they have low gravitational potential energy and puts them where they have high potential energy. So the ski lift is the analogy for the battery. And one value of this analogy is that it helps you avoid a common mistake. Over and over again, I see students look at a circuit like this, where this is the battery, and tell me, oh, well, this delta V bat, that's the voltage that's applied across each of these resistors. Well, no, that's nonsense. That's like saying you go 500 meters up on the ski lift, you come 500 meters down one piece of hill, and now 500 meters down another piece of the hill, and somehow arrive back at the bottom of the ski lift, even though you've come back down twice the distance you went up. Well, it makes no more sense in the circuit than it does in thinking about the hill. And if you think about the hill, you can avoid that sort of mistake. So now we come to the idea of what resistance is. If you take two identical batteries and you connect them to two different wires or resistors, so you've got the same voltage being applied because these are identical batteries, but you're going to find that you will have different currents. Remember, the battery doesn't supply current, it supplies voltage. The current that results now depends on what you hook it up to. And so this is, again, sort of like the ski hill. I can't carry this analogy much farther. It's going to be very valuable in the next unit, but I'm about to push it about as far as I can in this unit. If you have a hill with a lot of really twisty, long runs, then skiers who arrive at the top take a long time to get back down. And so most of the skiers will be out on the runs at any given time, not on the lifts. And so the rate at which they're arriving at the bottom of the lift and going up is low. But you can have a hill of the same height with the same number of skiers on it, but if the runs are straight and wide, skiers who get to the top arrive back at the bottom very quickly, and you have a larger number of people per unit time going back up on the lifts. And so you get a different skier current, even with the same number of skiers and the same height of hill. So similarly, there are factors which affect how much current flows through a wire, and they include the length of the wire or the resistor. Longer wire causes less current. It's harder to push current through a longer wire. The thickness of the wire or resistor. Thicker wire means more current. It's easier to push current through a thick wire. And also what the wire is made out of matters. Now we can define resistance. What you find when you do experiments is that the current is proportional to the potential difference applied across it. So here's the current through the wire, here's the voltage across the wire, and this number here is now the resistance of the wire. So the current is proportional to the voltage. In other words, if you plot I versus delta V, you'll see a straight line, and it has some slope, and we define that slope to be 1 over the resistance. Notice that means large resistance for the same delta V means a smaller current. That's why we call it resistance. If it's big, then the wire resists having charge pushed through it. And this law only applies to things that are called ohmic materials. Wires and resistors are made out of ohmic materials, but many other circuit elements do not behave this way. For example, diodes and transistors, and we've already seen that the relationship for delta V for a capacitor is different from this too. The one final piece of this is the role that the material plays. We already saw that longer wire means less current, or in other words, a longer wire must result in a larger resistance. Thicker wire means more current, or in other words, a smaller resistance. And so it turns out that the resistance is in fact proportional to the length of the wire and inversely proportional to the cross-sectional area of the wire. So that means R is proportional to L over A, and of course there has to be a proportionality constant. Fundamentally, that'll have to do with our definition of units. So there's the resistance, and notice it's a property of the wire. Various other properties of the wire, its length and cross-sectional area, factor into calculating it. Whereas this number, this variable rho, refers to what's called the resistivity, which is a property of the material the wire is made out of. As usual, when we meet new quantities, we should talk briefly about their units. So solving for the resistance, which is a new unit for us, it's a delta V over a current. And so that tells you that resistance is in volts per amp. And we define that as ohms, which we represent with this capital letter omega. So now you can see that the resistivity is going to be resistance times area over length. And so a resistance we know is in ohms, an area is in meters squared, and a length is in meters. And so a resistivity is in ohm meters. I'm just going to do a couple of quick calculations with these to show you how these sorts of numbers come out. So resistances vary a lot. The resistance of copper, which is a very, very good conductor, is given here. Nichrome, which you probably don't know about, but it's somewhat high resistance metal, often used in heating elements and things like that, has a resistivity that's about 100 times larger than that of copper. So let's talk about making a resistor out of nichrome. One way resistors are made is that you take a long thin wire and you coil it up into a tight coil so that it's nice and small, and you wrap it in plastic or something to protect it. So here we have a 20 centimeter length of nichrome. The radius is 0.1 millimeters. That's a fine, about 36 gauge wire. And you make a resistor out of this. So the resistance of that resistor is just going to be the resistivity of the nichrome, so 1.5 times 10 to the negative 6 ohm meters times its length, 0.2 meters, all over, and this is presumably cylindrical, right? So pi times r squared, so 0.0001 meters squared. And if you plug that into your calculator, you'll find these meters all cancel, and you are left with around 9.5 ohms. And so if you now take a 1.5 volt battery and hook that up to this resistor, you're going to find that your current is your 1.5 volts over your, I'm going to call it 10 ohms, and so you get a 0.15 ampere current.